Is it this one?
No, you did.
Wait, but doesn't it not record this thing though?
Shit.
Hey! Hey! No foul language in my classroom. Come on, you dreher.
About a population proportion of which, again, zero.
I liked it before you hear
So
this.
let's see what it says here. It says a test statistic measures how far a sample statistic, okay, so that's either an x-bar or a p-hat, diverges from what we would expect if the null hypothesis HO were true in standardized units. That is, in general, a test statistic can be found.
It's basically like a z-score. You find what.
Oh, good.
Yeah.
Something else I don't understand.
Okay, well, z-score literally it just tells you how many standard deviations away it is from the mean. This tells you how far away a statistic is from the parameter based on standard deviation. So it's like the same thing. It's how many standard deviations away it is from the whatever statistic it is. It could be a parameter, it could be an x bar, or it could be mean, whatever. That makes sense. Okay. Hey, Mr. Mill. Okay, she's not in here now.
This classroom.
No, she went that way.
I can give her a message for you if you'd like.
Okay, no, I just didn't know if she needed a laptop sleeve or anything.
Okay.
Tell her if she needs a laptop sleeve or a Ziploc bag, email me, and I'll run it back down.
Did you pause the recording?
I do not. But, I mean, do you want me to actually explain it?
No, you can keep going. I'll just grab myself a seat.
Do you want me to explain it then? Okay, so like, a z-score. Let's say the mean is 1, and the value is 1.2, and the standard deviation is, let's say, 0.5. All right, so 1.2 minus 1, because that's the value you're given, minus the mean.
0.7.
No, it would be 0.2. 1.2.
Oh, I
Yeah.
thought you said
Minus
0.5.
That'd be 0.8. I mean, that would still be 0.8.
Well, I got to keep 1.2 minus 0.5.
Oh, I thought you were meaning 1.2
so
or 1 minus 1 or
Basically,
0.2.
like statistic measuring how far a sample statistic diverges. So, like, how much different it is than we expected from the.
Okay, so let me put it this way. So, like, the standard deviation is going to be a number. It's going to be whatever number. Let's just say, like, it's 5. Let's say the parameter is, like, 10 or something. But the statistic you find is 13. So 13 minus 10, that would be the difference between the two. That's, how far away they are numerically, algebraically. That's how far away they are. That would be 3/5 of standard deviation.
Oh, they said 10.
Yeah, it's or 13 minus 10. Those are two values. Its standard deviation is 5. Just for example.
Yeah.
So
that would be how far the test statistic is away from the mean.
yeah,
Alright.
that's how many standard deviations it is away. 3/5 of 1. Same thing for a z-score. That's how many standard deviations it goes away for that. Same principle. I'm assuming it's the same principle.
By the general equation right here. Okay, so this test statistic,
Mr. Noel has a message. I'll pause it this time. Oh, it was still going. All right, whatever.
right here, it's going to depend on two things. If it's a proportion, the test statistic would be
That's
z,
like the core class.
or if it's a means problem, the test statistic would be a t.
And we know that already.
And so before we move on to the formula here, let's kind of review what a z-score was, so that can help you understand this a little bit better. So
z-score. How
when
old
we
is that?
talked about z-scores way back a long time ago, alright,
Not long. My crush.
we talked about how far a person, or what a person's z-score was. It depends where it fell. Okay, so we said before, this
Give us
is just
minus
some
like a
value, we'll just call it x. You would say, okay, I need to go from the value x minus where the mean was, right there, and then divide by the standard deviation. So a z-score is how many standardized units
So that's
the way to
Okay,
hand
now
calculate
you,
That's the way to hand calculate it. But how do what number would I take and go find it on the z table to find the z-score?
So you would find the number.
Oh, so plug into that formula and then find it on the z table?
Yeah, and that'll give you your percentage.
Yeah.
is a way from the center. Now these stand.
I knew there was a way to hand calculate z-scores, because we talked about that's the hard way.
I thought we got that when we went in.
That's exactly what I found out, yeah.
Oh.
Yeah. So instead of doing the calculator thing, you run the chart. Yeah.
Standardized units. Okay. The standardized units was the number of standard deviations. So for example, an IQ example, so maybe someone has an IQ of 132, it means 100, let's say the standard deviation is 16. And to find their z-score, we will take 132 minus 100 over 16, which will equal 32 over 16, which will equal 2. So this person that scored 132 actually has a z-score of 2, which means there are 2 standard deviations above the mean, which is fairly good. Okay. Well, now, instead of having this was in a population distribution, now let's put it in the context of a sampling distribution. It's easier to illustrate with means, so we have a sampling distribution here. Okay. Each one of these things is like an x-bar, and so on and so forth, and right down the center, that's the mu of the x-bar.
That's a big curve.
It's real thicky.
And it's going to be some value that we get out of HO in a hypothesis test. Hypothesis. So we're going to take a sample. Alright, we're going to find the mean, for instance. So to find the standardized score, or the test statistic here, find the test statistic, we would say, okay, where's our mean? Minus what we think the mean of the population is, so we'll call that mu naught. So this is some mu naught. There, maybe it's 100, or whatever it is.
No, he's just doing an example with a sample. Because there are different terms. So that one would be mu, because mu, yeah.
Over the sigma of the x-bars. So we're saying how many standard deviations.
Yeah, because HO is for samples. Or HO is for, sorry, it's for population. But he's saying that the mean, the mu of the sample, because it's mu sub x bar. So it's the mu of these samples. So the mean of these samples is the HO. Yeah.
Is the x-bar above or below the hypothetical mean. So it's the same idea.
Like you said, it's the same idea. This time it's just in terms of sampling distribution. And yeah, he's doing that. Yeah, he's doing that one. I think he meant the bottom one. My bad. Yeah, he's just doing that one in terms of what we would use, because we would use the the null hypothesis, or the I guess the mu sub null or whatever, and you would subtract it from whatever value we get. Obviously divided by standard deviation.
It's exactly the same idea. There's parallels between sampling distributions, test statistics, and just normal old z-scores. And now, in the case of the means problem, this test statistic will be t instead of z, because this has a t distribution instead of a z distribution. So hopefully that made a little bit of sense. So, the best way to understand these is to do a few problems. In section 9.2, they just want us to focus on population proportions. Okay, so here's our test statistic. So let's see what that says. We have our statistic. Since it's a, well, first let's talk about what. If it's a proportion, we're always going to use z with proportions. So we're going to take our sample statistic, our sample value, minus where we think the true row is, the true center. Okay, so like in our sampling distribution here, that's a normal curve, it's a z curve.
And that would be the null hypothesis.
We think the row is right there. Remember, that's the same thing as saying the mu of the p-hats. And so it's some value that we think it is. Alright, then we're going to take a sample. So we're going to get a p-hat. This is made up of a whole bunch of p-hats. We're going to say how many standard deviations is the p-hat away from what we think the center is. That's what it does. We take our p-hat minus this and divide it by what we think the standard error essentially based on this value. Where we think what we think the row is. Row none, that's just it.
Do it. I mean, yeah, the principle is the same. Yeah, the square root thing, that's standard deviation. The formula for standard deviation if you have the proportion. Yeah.
Is a place for a number. And even says here that p naught is the numerical value given in the hypothesis. So the best way to do this, like I said, go through an example. So this first example, it says a Gallup poll report on a national survey of 1,028 teenagers, the survey, so that's my sample size, revealed that 72% of teens said they rarely or never would argue with their parents. So this is a sample portion of p-hat. So the p-hat there is 0.72. It says Yvonne wonders whether this national result would be true in her daughter's high school. So she surveys a random sample of 150 students at her school. So this refers to a larger survey. It's a larger survey. Okay. So this is a different type of N. Alright, so that's a sample for her school. It said 96 students in the sample said they seldom or never argue with their friends. So the p-hat we got, or she got at her school, would be 96 over 150. If you want to change that to a decimal, just so we calculate 96 divided by 150, and that's going to be 0.64. It says write the null and the alternative hypothesis. Well, so the null is the HO. Alright, so before she took this survey, it says Yvonne wonders whether this national result would be true. So she's wondering if that's true from the national sample. So she's going to assume a row of 0.72. Remember that these always have to be parameters. Okay, so that's what she thinks it's the same. So if it's not the same, that means it wouldn't equal 0.72. Right, we always want to identify what the row represents, where a row is the true proportion of students in Yvonne's school who rarely or never argue with their friends. So always identify what the parameter means. Now it says calculate the test statistic. So since this is a proportional problem, it's going to be a z. So we're going to take the p hat, which we found to be 0.64, minus the rho naught. This is the rho naught value. All over the square root of the rho naught, the assumed center. So we're assuming the center is 0.72 times 1 minus 0.72 all over, okay, the sample size, her sample size, which was 150. So this one doesn't matter, that was from the national. Okay, now this did matter because that's the what she had to go on. And so we're going to assume that turns into the row. Alright, so we can do this and we'll set up our calculator. We can just do set up a fraction. 0.64 minus 0.72 all over base square root. Set up another fraction. 0.72 minus 0.72 over 150. Now before I hit enter, some common mistakes that students make, they'll put the 0.64 there. Okay. And you should not do that. It's the assumed center, is what the rho actually is. Okay, so we're assuming rho is 0.72. Just hit enter there. So my test statistic would be negative 2.182. So on our graph, we're assuming the center is at 0.72. Again, this is the sampling distribution of p hat. Okay. We got a p hat of 0.64, which is less than 0.72. And when we calculate the test statistic, this right here, and in that distribution falls 2.182 standard errors or standard deviations below the assumed center. So the next part says find and interpret the p-value. So the p-value would be the area. Now, this is a two-tailed test. So after I find this area, I actually have to double it because there's a mirror on the other side. Okay. There's a mirror on the other side. So once I find this area, I gotta double it. So how am I going to do that? Well, I'm going to store this. I'm just going to store it as z, because it's a z test statistic. And I know that this is a normal curve. And this is a normal curve. Alright, so I'm going to go to my normal curve. I'm going to go normal CF. Alright, I'm going to go from negative infinity up to my z value. And then the standard normal curve, the mean is 0, and the standard deviation is 1. And paste. And make 0.0145. This area. And since it's a two-sided test, I gotta count the other tail. So I gotta multiply that times 2.
Okay, so all that just to say, we're basically doing the same thing we've always done. We're standardizing it by putting it in terms of z, like a z-score, because it's a proportion problem. Because it's a proportion problem, we're doing a z-score. If not, we would do t-score for a mean problem. And we're using the formula that says up there, p hat minus p null. And basically the p null is always going to be the thing they give you first, the thing that the sample study or whatever is going to be based off, which would be 0.72, because that's what the Gallup poll report said. But then the rest of the information will be based off the sample that they conduct to disprove it or prove it or whatever. And that was the 96 students out of 150, 0.64, and so you plug that onto your formula. P hat would be 0.64, or p null would be 0.72. You find standard deviation and then z-score and everything. I guess it's also important to note that this is a two-tailed test, just because they didn't state whether it was any greater or different. It was just, or not any greater or less than, it was just different. So
The only other thing we would want to add is trying to make the calculator easier. You would argue, take notes.
What is huh? What?
Hunter, you're being summoned.
Okay. Did you my calculator?
Uh-oh. Hunter, you do it.
What am I?
See, go to say calculate normal CDI,
Oh.
but don't change it to.
So
But don't change it to
Leave
the.
it to fully normalize it.
yeah, when you're doing the standard deviation though, you still have to calculate that anyway.
Oh, I guess that.
Yeah, so might as well just calculate that thing.
Oh, that's straight, never mind.
Yeah.
That's
that-
straight, never mind. I was gonna try to make it easier,
I think
to have to like not normalize it and it's still good for these score.
Yeah.
But because that standard deviation, right, I think.
So, I mean, what you're trying to do is just, use the number that they give us, but because they don't give us standard deviation, we have to calculate that. And we're already doing that when we normalize it.
Yeah,
I just followed the dude correctly to figure out how to do it without normalizing.
yeah, well, like he's saying, you know all the things, but you don't know the standard deviation, heck, if you're actually gonna calculate that. why
Might as
not?
well.
Yeah.
And then the p-value, I guess we can go back to that. The p-value was, what was it? 0.29, I guess 0.291. And because that's going to be less than 0.05, assuming that's our alpha, they didn't give us one, so we just assume that's our alpha. We have to assume that doesn't disprove the null hypothesis, but that gives us evidence to just
It's not true.
He was like,
reject the hope. So yeah.
0.029.
yeah, you could skip all of 9 1, that's basically all of the yesterday.
Oh, okay.
Well, there was a type 1 and type 2 there. They can tell you that in a second. Finish this one and then they'll tell you.
So that is what the p-value would be. So it also told me that, so we found it, we have to interpret it. There is a 2.9% chance that we would observe a sample proportion as extreme or more extreme than that observed. So this is what we observed. So this extreme or more extreme than that observed. If the true proportion were 0.72.
Oh god.
So if the real proportion was 72% at this school, okay, there's only a 2.9% chance that we would get a key hat that far away, or more far, on both sides. On this side, that's a difference of 0.8. taking this because it was a 2.9% chance, we would observe let's say a p hat. Say a p hat less than 0.64 or a p hat greater than 0.80 if the true proportion were 0.72. So you can be more specific if you want.
So basically, that's all to say, like, remember from the thing, I guess, from the other day, like, it was low, reject the hoe. Basically, because of the rarity of this, because there's a percent chance less than 5%, we have to assume that this helps disprove the null hypothesis, because if it were likely, it was like 0.85. If it were something very likely, then we would say, okay, fine, I guess it has to be true. But because it's so unlikely and it did happen, that's why we have to reject the hoe, I guess.
And I think Louise is right. I don't like the way he necessarily worded it. I would have, the way we've been saying, like, he is less than alpha, I think I would have said 0.29 is less than the 0.05. And I would have put in the P and the alpha values, and then I would have referenced back to the hoe. We reject the fact that the true proportion of students in one school was supposedly 0.78.
I do like the fact that he said, though, like, it could be less than 0.64 because that's what we calculated, the fact that it's less than that area or greater than the area of 0.8. So I think that's also important to
I do
input.
like that too. I do like that. Well, but again, if you were summarizing I guess the whole opposite, if the P is low, we've rejected the hoe, which means we don't say accept, but we're accepting the ha. So, yeah, that would be.
Yeah, I mean, just to add, like,
Is it
words to it.
We fail to reject the law.
Well, since we rejected the hoe, I would put assume, and then instead of saying assume ha, I would put assume and then words that mean the ha, like English that means the ha. And the true proportion of students is not 0.72.
Yeah.
He is low, reject the hoe, assume ha, but
2.9% chance that would happen. Right. Really small chance. So eventually we're going to say, we're probably not believing that anymore. That's probably not the real or the true proportion. Because that is such a low chance to happen. It's such a low chance that I would repeat that far away. So, you might just say, well, it's only 8%.
Yeah.
Oh my gosh, this is so fun.
Do you want to key on the multi-step thing?
No, let's not do that. Let's, so I'm going to explain the type 1 and type 2 to Louise from yesterday,
Oh, yeah.
and then we can do the worksheet. So you can do that worksheet really fast, but I get question that
Alright. I can do type 1, type 2.
Yes, go ahead.
Okay. Type 1 is like Harambe. He was innocent, but everyone called him guilty. He was persecuted.
Persecuted.
And then
Yeah.
there was no persecution.
Oh, man, she's not recording.
And then type 2 is like O.J. Simpson, where everyone knew he was guilty.